Stars provide an incredibly beautiful backdrop of the sky, so it's only fitting that they have a dramatic death. But how exactly do they die? Stars light up due to a process called nuclear fusion, in which two hydrogen nuclei join together to form a helium nucleus. This results in the release of energy in the form of light and heat. But as with most fuels, the quantity of hydrogen in stars, while present in amounts allowing them to remain alight for hundreds of millions of years, is finite. When all that hydrogen runs out, we call that the death of a star. Stars of all masses undergo the same initial stage following the depletion of hydrogen. The lack of nuclear fusion gives way for the star's gravitational force to collapse the core. This causes fusion to happen in the shell surrounding the core, releasing energy which causes the star to expand significantly to hundreds of times its original size, becoming a red giant in the case of low-mass stars like the Sun, and red supergiants in the case of more massive stars. Our own Sun will expand large enough to eat up Mercury, Venus, and probably Earth. Stars remain in this phase from anywhere between a few million to a few billion years, and it's after this stage that the process of the death of the star differs depending on its mass. Red giants shed their outer layers to eject gas and dust which form a shell around the star. Ultraviolet radiation from the star's core causes these gases to glow in different colors, becoming a planetary nebula. These nebulae don't last near as long as the red giant predecessors, usually lasting only a few thousand years as the gases slowly scatter into space, leaving behind what was the star's core, now called a white dwarf, all alone emitting what little thermal energy it has left. The stages following a red supergiant are much more violent and dramatic. As red supergiants, stars fuse all the helium created from the fusion of hydrogen to create several of the larger elements like carbon and oxygen, which themselves then fuse. This keeps going on with larger elements until the supergiant's core is mostly iron, at which point fusion stops and no more energy is released. The enormous gravitational force of this now iron core would cause the star to collapse in on itself, significantly increasing its density and subsequently releasing a sudden and huge amount of energy, leading to the explosion of the star, which we call a supernova. Supernovae aren't your average explosions. Their luminosities are many billion times that of the Sun, allowing you to see a supernova take place with the naked eye. In addition, enough energy is generated to allow for the nuclear reactions that produce many of the heavier elements like gold, zinc, tin, silver, uranium, among others. These nuclear reactions require such immense amount of energy that they can only happen during a supernova. This means that the gold used in jewelry, the tin in cans, and the mercury in thermometers all came from dying stars. Following a supernova, the core, if it hasn't been destroyed by the explosion, will collapse, becoming one of two greatly dense bodies depending on the core's mass. If its mass is up to 3 times that of the Sun, it will become a neutron star in which almost every proton and electron was crushed into, you guessed it, neutrons. If the core's mass is more than 3 times that of the Sun, it would collapse into a size even smaller than a neutron star. This means that so much mass is being packed into so little space that the core's density would be absurdly large, giving it an unbelievably strong gravitational force. So strong, in fact, that even light can't escape its pull, and that's how black holes are formed.